Buenas noches! January 18th. Tonight we're going to study generalization of Diophantine equations to polynomials. The most general case is where polynomials are exchanged by an Euclidean domain. What is an Euclidean domain? Exercise. Let's solve a txt plus btyt equals to 1, where x from t is a polynomial of degree 5 and y of t is a polynomial of degree 5. I don't like numbers, I don't like examples, so I've taken the first primes 2, 3, 5, 7, 11, 13 for y, 17, 19, 23, 29, 31, 37 for x. 1 is a unit in Zx, the polynomials with integral coefficients. So there is a solution. We prove it. There is a single, an ordinary solution that will lead to a general solution in 50 steps. Our algorithm, as we did in another video before, is divide x by y. Stop when the remainder is of degree 0. So we're going to have q0, r0, a0, b0. Then we'll add x1, y0, y1, r0. Then we'll divide x1 by y1. We'll have a1, b1. After that, we'll have a2, b2, a3, b3, a4, b4, a5, b5, and the remainder is indivisible. So break and return B, return A. x0 equals to x, y0 equals to y. The quotient is k0, the remainder is r0. Who is k0? Divide 17 by 2. Who is r0? Take x0 and subtract 17 over 2 by y of t. Do the calculations, and we'll have a polynomial of degree 4. Here I indicated coefficient of 1, coefficient of t, coefficient of t2, coefficient of t3. The coefficient of t4 is 19 minus 51 over 2. Now let a0 be 1, let b0 be minus q0. Divide x1 by y1, where x1 is y0 equals to this, y1 is r0 equals to a polynomial of degree 4. Here I did the calculations. Minus 13 over 2. Let x1 be the product of the quotient by y1 plus the remainder 1. Q1. Who is the quotient? Divide 2 by 13 over 2 is 4 over 13 with minus sign plus t. Who is r1? Is x1 minus 4 over 13 times t times y1. Doing the calculations, dividing the leading coefficient of r1 by y1, 3 times 13 over 2, which multiplied by y1 cancelling t4 leads to a polynomial of degree 3. Dividing a polynomial by another polynomial is fundamental. It's not high school. A1 equals to minus A0 Q1. B1 equals to minus B0 Q1 plus 1. So I remember we're using the algorithm. Who is x2? Y1, degree 4. Who is y2 is equal to r1 equals to a polynomial of degree 3. Divide x2 by y2, giving quotient q2 and remainder r2. q2 is a constant times t plus another constant, dividing the leading coefficient by the leading coefficient of y, 13 over 2 times 52 over 20,001. You'll have 2 over 117. Who is R2? Do the same calculations and you have this two-lined degree 2, the coefficient of 1, the coefficient of t, the coefficient of t2, plus 1t, t2 will give R2. Here I quit it. Let the computer do that for you, not me. Now let A2 be equals to A0 minus A1 Q2. B2 equals to B0 minus B1 Q2. And who is x3? It's y2, a polynomial of degree 3 indicated by A, B, C, big D. Who is y3? It's r2, a polynomial of degree 2, et2 plus ft plus big G. So degree 3, degree 2. Degree 3, degree 2, x3 divided by y3 equals to quotient q3 and remainder r3. Divide a by e times t plus the remainder b over e minus af times e2 is the quotient q3. Who is r3? Do the calculations and you'll have a polynomial of degree 1. Coefficient of z1, coefficient of t, coefficient of 1, coefficient of t. Who is a3? A1 minus a2 times q3. Who is b3? It is b1 minus b2 times q3. Who is x4? It is y3. Who is y4? Is r3. Here we have a polynomial of degree 2 divided by a polynomial of degree 1. So, repeating EFG and repeating R3. C minus AG over 3 minus constant times F equals to, summarizing, H. X4 equals to Q4, Y4 plus R4. We divided X4 by Y4. Who is Q4? Divide E by H times T plus 0. Who is R4? Take Ft plus G and subtract E over H times T times J. Now A4 is A2 minus A3 times Q4. B4 is B2 minus B3 times Q4. Who is x5 is y4 equals to ht plus j, as we already know ht plus j. Who is y5 is r4, summarizing j equals to m and L equals to F minus EJ over H. Who is X5 divided by Y5? The quotient is Q5 and the remainder is R5. Who is Q5 divided H by L plus 0? Who is R5? J minus HM times divided by L. Who is A5? Is A3 minus A4 times Q5. Who is B5? Is B3 minus B4 times Q5. Therefore, multiplying A5 by X5, summing with B5 Y5, we will have R5. But we want 1. We want A of t, x of t, b of t, y of t equals to 1. So divide by R5. A single solution is A of t equals to A5 over R5. And b of t is B5 over R5. Whenever we add b of t to a times a constant, we have to subtract e of t from b times a constant. So a equals to a of t plus constant b of t, and b equals to B5 over R5 minus A of t times constant. Out of charity, there is no salvation at all. Next time, we're going to study more general case. There's life after polynomials. There are Euclidean domains of modulo ideal rings.